There is a place in the sky, 5,000 light years away, where the temperature drops below the cold of space itself. A single degree above absolute zero, quietly held in the constellation Centaurus. Welcome to the Sleepy Lab. Tonight, we drift toward the coldest place in the universe and the gentle warmth that fills the space between the stars. If this channel helps you rest, consider subscribing, one sleepy soul at a time. Now, let's begin. The Boomerang Nebula. It carries a soft name for something so extreme. This cloud of gas and dust is, as far as we can tell, the coldest known natural place in the entire universe. Roughly 1 degree Kelvin, 1 degree above the point where all thermal energy would simply cease. To feel how cold that is, you would need to travel far below anything Earth has ever known, far below the frozen plains of Antarctica, far below the surface of Pluto, even below the faint warmth that fills the emptiness between galaxies. 1 degree Kelvin is a kind of cold that barely exists. And yet, it does. At the heart of this nebula, a star is dying. Not violently, not all at once, but slowly, shedding its outer layers into the dark. Gas streams outward from this fading star at about 164 kilometers every second, a tremendous, silent exhale spreading into the void. And it is this expansion that creates the cold. When gas expands rapidly, it cools. You may have felt a faint version of this on a warm afternoon, the slight chill when air rushes from a tire valve. The Boomerang Nebula does the same thing, only on a scale almost too large to hold in the mind. Billions of kilometers of gas, thinning and cooling as it races outward, acting like a kind of cosmic refrigerator, drawing heat away from itself faster than the universe can warm it back up. This is what makes the Boomerang Nebula so remarkable. It is not simply cold because it is far from any star. It is cold because it is actively making itself colder. And that matters, because the universe, as it turns out, has a minimum temperature. Everywhere you go in the cosmos, no matter how far from the nearest galaxy, no matter how deep into the emptiest void, there is a faint warmth. It is quiet and ancient, and it fills all of space without exception. This is the cosmic microwave background, a soft glow left over from the earliest moments of the universe, and it holds a temperature of about 2.725 Kelvin. Think of it as a kind of floor, a gentle baseline warmth that touches everything. Every grain of dust drifting between the stars, every frozen rock at the edge of the solar system, every molecule of hydrogen floating alone in the dark between galaxies. All of it is bathed in this faint, ancient light. No natural place in the universe can be colder than this background warmth, unless something is actively pulling heat away, unless some process is working against the warmth, pushing the temperature lower than the cosmos itself allows. The Boomerang Nebula is one of those rare places. Its rapid expansion overwhelms the gentle warmth of the background radiation, and the temperature drops below what should be possible in open space, 1 degree Kelvin colder than the afterglow of creation. Now, let us rest here for a moment with a quieter idea. There is a point on the temperature scale where cold reaches its deepest meaning. It is called absolute zero, 0 Kelvin, or minus 273.15 degrees Celsius, and it represents something profound, the total absence of thermal energy, a place where, in theory, all atomic motion would stop. Every vibration, every tremor, every restless jostling of particles would fall still. But even there, at the very bottom of the scale, the universe does not allow perfect silence. Quantum fluctuations, tiny and irreducible, would still persist, a faint hum beneath the stillness, as if the fabric of reality itself cannot quite hold its breath. And the third law of thermodynamics tells us something gentle but firm. Reaching absolute zero exactly is physically impossible. You can approach it, you can come breathtakingly close, but the final step, that last fraction of a degree, always remains just out of reach. It is a boundary the universe has drawn, not with force, but with quiet certainty. So the space between galaxies, the vast and seemingly empty dark, is not truly empty at all. It is filled with this faint afterglow, the cosmic microwave background, a whisper of warmth that has been traveling since the universe was young. And the story of its discovery is a gentle one. In 1965, two scientists named Arno Penzias and Robert Wilson were working with a large radio antenna in New Jersey. They were not looking for the edge of the universe. They were simply trying to calibrate their instrument. But no matter where they pointed it, no matter what they did, there was a persistent hum, a faint, steady signal coming from every direction in the sky. They checked their equipment. They cleaned the antenna. They even removed a pair of pigeons that had been nesting inside the horn and carefully cleared away the droppings the birds had left behind, thinking perhaps that was the source of the noise. But the signal remained. It came from the north and the south, from the east and the west. It was everywhere, and it was always the same. And slowly, carefully, the realization settled over them. They were not hearing interference. They were hearing the universe itself, the faint, cooled remnant of the light that filled all of space when everything began. That light was once searingly hot, thousands upon thousands of degrees, a blinding fog of energy that filled the young universe from edge to edge. But over 13.8 billion years, as space expanded and stretched, that light cooled, slowly, gently, degree by degree, until it became what it is tonight, a soft glow at 2.725 Kelvin, too faint for our eyes, but detectable by patient instruments and quiet antennas pointed at the sky. It is still here, all around us, passing through this room, through the air above your bed, through the walls and the glass and the dark outside your window. A lullaby from the very beginning of time, still playing, still cooling, still holding the universe in its faint and ancient warmth. And somewhere, 5,000 light years away, the Boomerang Nebula is still expanding, still cooling, still 1 degree above the deepest cold the laws of physics will allow. A dying star, breathing out into the dark, making the coldest place we have ever found. Let that settle over you now. There is no hurry. The cold is patient, and so is the night. And while that nebula breathes its cold breath into the constellation of Centaurus, there are other places, closer to home, where the cold runs deeper than you might expect. Consider the moon, our nearest neighbor in space, bright and familiar. A world we have watched from fields and rooftops and bedroom windows since we were children. It seems so well known, so thoroughly seen. And yet there are places on the moon that have never been seen at all. Not by human eyes, not by sunlight. Near the lunar poles, deep inside certain craters, there are shadows that have not lifted for over 2 billion years. 2 billion years of unbroken dark. The rims of these craters rise just high enough to block the sun, which hangs so low near the poles that its light never reaches the floors within, and so the cold is gathered there, slowly, completely, settling into the dust and the rock, like something that has always belonged. In those permanent shadows, temperatures drop to about 33 Kelvin, colder than the surface of Pluto, colder than the space between the outer planets, a cold so deep it can trap molecules that would otherwise drift away into the vacuum. And it has. Multiple spacecraft missions have confirmed that water ice exists inside these craters. Ancient ice, carried there by comets or drawn from the lunar interior long ago. Ice that has remained frozen in the dark for longer than complex life has existed on Earth. The coldest measured spot on the moon lies inside Hermit crater, near the North Pole. About 26 Kelvin, a temperature so low it rivals the cold of deep space itself. And all of it just 3 days travel from where you are lying right now. It is a strange thought that the coldest place in our immediate neighborhood is not some distant world at the edge of the solar system, but a quiet crater on the moon, a place you could almost point to on a clear night. Pluto, that small and distant wanderer, averages about 44 Kelvin on its surface. Cold, Certainly, unimaginably cold by any earthly standard, but warmer than the deepest lunar shadows, warmer than Hermite Crater by nearly 20 degrees. Farther out, Neptune's largest moon, Triton, drifts through temperatures of about 38 Kelvin. Its surface is a frozen plain of nitrogen and methane ice. And yet, even there, something stirs. Geysers of nitrogen gas erupt from beneath the surface, plumes rising kilometers into the thin sky before falling back as dark streaks on the frost. Cold enough to freeze the air we breathe into glass. And still, not quite as cold as a shadow on the moon. Uranus holds its own quiet record, the coldest atmosphere of any planet in our solar system, with temperatures dipping near 49 Kelvin in its upper clouds, a pale blue world tipped on its side, rolling along its orbit in a kind of slow, perpetual tumble, its coldest layers hidden beneath a calm and featureless haze. But to find the deepest cold in our solar system, you must travel much farther out, past the orbits of all the planets, past the scattered ice of the Kuiper Belt, out to the very edge of the sun's gravitational reach. The Oort cloud, a vast, spherical shell of ice and rock, stretching perhaps 2 light years from the sun in every direction, so far away that the sun, from there, would be just another star, a bright point among millions, offering almost no warmth at all. Out there, temperatures fall to roughly 4 to 10 Kelvin, just a few degrees above the cosmic microwave background itself, the cold of nearly empty space, the cold of almost nothing. And in that cold, comets wait. Trillions of them, as far as we can estimate. Small bodies of ice and dust and frozen gas, drifting in orbits so wide that a single trip around the sun can take millions of years. They are so cold that volatile gases, things that would boil away in an instant near the sun, remain locked in solid ice, perfectly preserved, for billions of years. They are time capsules, older than the Earth, older than the moon and its ancient shadows, carrying within them the original chemistry of the cloud that formed our solar system. And sometimes, very rarely, one of them is nudged, a gravitational whisper from a passing star, or the faint pull of the galaxy itself shifts its orbit just enough, and it begins to fall inward, slowly at first, then faster, drawn toward the distant warmth of the sun. As it approaches, the frozen surface begins to change. Ices that have been solid since before the Earth existed start to sublimate, turning directly from solid to gas in the vacuum of space, and that gas carries dust with it, forming a halo around the tiny body, a coma, and then, pushed by the solar wind and the pressure of sunlight itself, a tail. A glowing tail, stretching millions of kilometers across the sky. That is what we see from Earth when we see a comet, a visitor from the coldest edge of our solar system, briefly, beautifully warming, before it turns and falls back into the dark. But even the Oort cloud is not the coldest realm. Beyond our solar system, between the stars, there are clouds of gas and dust so cold and so dense that they block the light of everything behind them. Molecular clouds, vast nurseries of cold matter stretching across dozens of light years. Inside these clouds, temperatures can fall as low as 10 Kelvin, cold enough that molecules move with barely a whisper of energy, cold enough that atoms cling to tiny grains of dust and build thin mantles of ice around them, one molecule at a time. And yet, these are not dead places. These cold, dense clouds are where new stars are born. Deep within them, gravity slowly draws matter together, pulling gas and dust into denser and denser knots, until the pressure and temperature at the center rise high enough to ignite fusion, and a new star opens its eyes for the first time, flooding the surrounding dark with light and warmth. From the coldest places, the hottest things emerge. It is one of the quiet paradoxes of the universe that stars are born in the cold, that the fire begins in the dark, that the places where temperatures are lowest are the very places where everything begins again. Let that thought rest with you for a moment. The cold is not barren. It is not the end of things. It is a kind of stillness where the universe gathers itself, patiently, quietly, preparing for what comes next. And you, too, are settling now, letting the warmth of your bed hold you, letting the night do what it does so well. There is no hurry. The cold places will still be there in the morning, the craters on the moon still wrapped in their ancient shadow, the comets still drifting in their long, slow orbits, the molecular clouds still quietly collapsing, still building something new. Far out in the constellation of Orion, there is a shape you may have seen in photographs, a dark silhouette rising against a curtain of glowing gas, the Horsehead Nebula. It looks almost like a chess piece carved from shadow, and within its dense folds, temperatures hover around 12 to 20 Kelvin, cold enough that most gases have long since surrendered their motion, settling into a deep and patient stillness. The Horsehead is what astronomers call a dark nebula, a place where dust and gas have gathered so thickly, so densely, that they block the light of every star behind them. If you were to look toward a dark nebula with your eyes alone, you would see nothing. Just a patch of sky where the stars seem to vanish, as though someone had drawn a curtain across a window. There is one such cloud that does this with remarkable completeness. It is called Bernard 68, a small, dark molecular cloud drifting through the Milky Way, and it is so opaque, so perfectly dense, that almost no background stars are visible through it at all. In photographs, it appears as a hole in the sky, a circle of pure black surrounded by thousands of glittering points of light. It is not a hole, of course, it is a cloud, but one so cold and so tightly packed with dust that light simply cannot pass through. And yet, inside that darkness, something extraordinary is happening. In the cold cores of clouds like Bernard 68, on the surfaces of tiny grains of dust, complex organic molecules are slowly forming. Piece by piece, atom by atom, chemistry is unfolding in the dark, without heat, without light, without any of the things we usually associate with creation, just cold dust and time, and the quiet persistence of molecular bonds finding one another in the stillness. The dust grains themselves are almost impossibly small, typically only a fraction of a micrometer across, smaller than a wavelength of visible light, and yet each one carries a thin mantle of ice, water ice, carbon dioxide ice, sometimes ammonia or methanol, frozen coatings that serve as tiny laboratories where new molecules are assembled in the cold. It is a strange and humbling thought that the building blocks of complexity, the precursors of amino acids, the raw ingredients of everything that eventually becomes biology, can begin their journey on a speck of dust smaller than anything your eye could ever see, drifting through a cloud at 15 Kelvin in total darkness. Now, let yourself drift a little further out, beyond the nebulae, beyond the star-forming regions, into the spaces between the stars themselves. Interstellar space, far from any star, far from any warmth, settles to a temperature of roughly 3 Kelvin, just barely above the cosmic microwave background, that faint, ancient warmth that fills all of space, the afterglow of the beginning. 3 degrees above absolute zero. That is what the universe offers when nothing else is near. No star, no galaxy, no source of heat at all, just the quiet hum of the oldest light there is. But even this is not the emptiest place to consider. If you pull back further still, far beyond our galaxy, beyond the nearest clusters of galaxies, you begin to see the largest structures in the universe and the largest absences. Voids, enormous regions of space where almost nothing exists. The spaces between galaxy clusters, among the emptiest and coldest large-scale structures we know of. One of the most striking is the Botos Void, a vast, nearly empty region of space spanning about 330 million light-years across. Inside it, only a handful of galaxies have been found, scattered like a few grains of sand across a desert floor. The rest is silence and cold, and an almost incomprehensible amount of nothing. And yet, even here, the temperature does not fall below the cosmic microwave background. Even in the deepest void, the faintest warmth of the Big Bang still reaches, still fills the space with its gentle 2.725 Kelvin. It is as though the universe has a floor, a minimum warmth it will not surrender, not naturally, not without some active process to push the temperature lower still. Between these voids, stretching like bridges between the galaxy clusters, there are filaments of gas, long, thin threads of matter that trace the scaffolding of the cosmos. Some of these filaments carry gas at temperatures of about 100,000 Kelvin, which sounds warm, and it is, by earthly standards. But by the measure of intergalactic space, where gas inside galaxy clusters can reach tens of millions of degrees, 100,000 Kelvin is remarkably cool. Supercooled, even a kind of lukewarm thread woven through the fabric of everything. Together, the filaments and the voids, the clusters and the empty spaces between them, form what astronomers call the cosmic web, a vast, sponge-like structure that stretches across the observable universe. If you could see it all at once, from impossibly far away, it would look like a network of glowing threads surrounding dark bubbles, matter gathered along the edges, emptiness pooled in the centers, a pattern repeated on scales of hundreds of millions of light years. It is the architecture of everything, and most of it is cold, and most of it is quiet, and most of it is simply waiting. Now, let your thoughts turn to something smaller and stranger. When a massive star dies, when it collapses under its own weight in a supernova, what remains at the center is sometimes a neutron star, an object so dense that a single teaspoon of its material would weigh as much as a mountain. When a neutron star is born, it is unimaginably hot, hundreds of billions of degrees in its first moments, blazing with a heat that rivals the cores of the most violent events in the universe. But neutron stars cool over millions of years. They radiate their heat into the surrounding dark, slowly, steadily, and their temperatures fall from billions of degrees to millions to thousands to, eventually, just a few hundred Kelvin, still warm by the standards of deep space, but a shadow of what they once were. The oldest neutron stars in the galaxy have been cooling for so long that they are approaching the background temperature of space itself, fading, dimming, becoming harder and harder to detect, like embers buried in ash, still glowing, but only just. There is something almost tender about that, a star that once burned with the energy of a billion suns, slowly giving its last warmth to the void, degree by degree, over timescales that dwarf the age of the Earth. And the cold receives it all, patiently, without hurry, the way the night receives the last light of evening. Let that image settle over you now, the slow cooling of ancient stars, the quiet dark of nebulae where new molecules are forming, the vast, empty voids where almost nothing stirs, and through it all, the faint, steady warmth of the oldest light in the universe, holding everything, touching everything, 3 degrees above absolute zero, everywhere at once. You are warm, and you are still, and the universe is very, very old, and very, very patient, and there is nothing you need to do right now but rest. Rest, and let the story carry you a little further. White dwarf stars follow a similar path, though they take even longer to walk it. A white dwarf is what remains after a star like our sun exhausts its fuel. It no longer burns, no longer shines by fusion. It simply glows with the heat it has left, a dense, quiet ember the size of the Earth, slowly releasing its warmth into the dark. The coldest white dwarfs we have found still glow at a few thousand degrees Kelvin, warm enough to emit a faint, pale light, but nothing compared to what they once were. They have been cooling for billions of years already, and they have billions more to go. There is a name for what a white dwarf would eventually become, if given enough time: a black dwarf, a star that is cooled so completely that it no longer emits any light at all, no heat, no glow, just a dense, dark sphere drifting silently through space, invisible against the black. But here's the quiet part, the part worth holding gently as you lie still. No black dwarf has ever existed. The universe is not old enough, not nearly old enough. It would take trillions of years for even the oldest white dwarfs to cool that far, and the universe is only about 13.8 billion years old. So black dwarfs remain a prediction, a future that has not yet arrived, a chapter the cosmos has not yet written. Somewhere out there, the oldest white dwarfs are still faintly glowing, still giving off the last of their ancient heat, and they will continue to do so for longer than everything that has happened so far. Let that thought be soft. Let it be slow. The universe itself is cooling, not just its stars, but everything, all of it, together. Every photon of light traveling through space is being gently stretched, pulled longer and longer by the expansion of the universe. As space itself grows, the wavelength of light grows with it, and as the wavelength stretches, the energy decreases and the temperature drops. This is called cosmological redshift, and it has been happening since the beginning. The cosmic microwave background, that faint warmth left over from the earliest moments, was once a blinding fire. Thousands of degrees, filling all of space with light too bright to see through. But over 13.8 billion years of expansion, it has cooled to just 2.725 degrees above absolute zero, a whisper of what it was. And it will keep cooling. In the far future, as the universe continues to expand, the cosmic microwave background will fade further still, its temperature dropping closer and closer to zero, never quite reaching it, but approaching so gently that the difference would be beyond any instrument's ability to measure. Eventually, in a future so distant that numbers begin to lose their meaning, all temperatures everywhere may equalize. No hot, no cold, no difference at all between one place and another. No energy flowing from here to there, because there would be no gradient left to drive it. This is what physicists call the heat death of the universe. Not a dramatic ending, not a collapse or an explosion, but a slow, quiet settling, like a pond that has finally become perfectly still. Everything the same, temperature everywhere, forever. That is a long, long way from now. So far away that it belongs to a kind of time we cannot feel, only describe with mathematics. And even the mathematics grows quiet at those scales. For now, the universe is still full of difference, still full of warm things and cold things, still full of contrast and motion and change. And you are part of that, warm and breathing, resting in a world that still has so much happening. Let your breath slow just a little more. Closer to home, the cold can be remarkable too. The coldest natural temperature ever recorded on the surface of the Earth was minus 89.2 degrees Celsius, measured at Vostok Station in Antarctica in July of 1983. Deep winter, in the interior of the coldest continent, where the air is so dry and the sky so clear that heat escapes from the surface almost without resistance, radiating upward into the dark polar night. There is a place called Dome A, the highest point on the Antarctic plateau, where temperatures may drop even lower than what was measured at Vostok, but continuous monitoring there is difficult. The cold itself makes it hard to keep instruments running, hard to keep anything running. It is one of the most remote and inhospitable places on Earth, and yet it is still, by cosmic standards, extraordinarily warm. The average temperature of the Antarctic interior in winter is about minus 60 degrees Celsius, cold enough to make steel brittle, cold enough to freeze carbon dioxide from the air if conditions were right, but still roughly 213 degrees above absolute zero, a warmth that the Boomerang Nebula would never know. To go colder than nature allows on Earth, we need to build our way there. Liquid helium boils at 4.2 Kelvin, just a few degrees above absolute zero, and it is one of the most important tools in the science of extreme cold. It flows through the veins of particle accelerators, cools the magnets in medical scanners, and chills the detectors of space telescopes. Without liquid helium, much of modern physics would simply not be possible. But even 4.2 Kelvin is not cold enough for some experiments. There is a rarer form of helium called helium-3 with one fewer neutron in its nucleus. It is far less abundant than ordinary helium-4, most of it a relic of the early universe, and it has special properties at very low temperatures that make it invaluable. By mixing helium-3 and helium-4 together in a device called a dilution refrigerator, scientists can reach temperatures of just a few thousandths of a degree above absolute zero, millikelvins, a cold so deep that the atoms themselves begin to behave in ways that have no parallel in everyday life. They slow, they quiet. They begin to reveal the quantum nature that warmth normally hides. These machines hum softly in laboratories around the world, pulling heat away, layer by layer, approaching a limit that can never quite be touched. And there is something peaceful in that. The idea that absolute zero is always just out of reach, always one more step away, no matter how close you come, like a horizon that moves with you, not because it is far, but because it is a boundary woven into the fabric of things. You do not need to reach it. You do not need to reach anything right now. The cold is patient, and so is the night, and so is the slow turning of the earth beneath you, carrying you gently through the dark. There are other ways to chase the cold, quieter ways, that work not by mixing liquids, but by coaxing the very magnetism out of a material. In a technique called adiabatic demagnetization, a substance is first magnetized in a strong field, its tiny atomic magnets all lining up in neat rows, and then, slowly, the field is taken away. As the atoms lose their magnetic order, they absorb energy from their surroundings, and the temperature drops, not by degrees, but by millionths of a degree, drifting closer and closer to absolute zero, closer than almost anything else can go. It is a kind of patience made physical, a slow unwinding, a letting go. And then there is light. Not the warm light of a lamp or a star, but light that has been carefully shaped, tuned to a precise frequency, and aimed at atoms that are moving just a little too fast. When a photon meets an atom head-on, it pushes back, gently, slowing the atom down by the tiniest amount. One photon alone does almost nothing, but millions of photons, arriving from every direction, each one nudging, each one absorbing a sliver of motion. Together they bring the atom nearly to a standstill. This is laser cooling, and it sounds almost paradoxical, using light to make things cold. But it works because temperature, at its heart, is just motion. And if you can slow the motion, you lower the temperature. There is a limit to how far this can go, a boundary called the Doppler cooling limit, where the very act of absorbing and re-emitting photons introduces a small randomness that prevents the atoms from getting any colder. For most atoms, this floor sits at a few hundred microkelvins, a few hundred millionths of a degree above absolute zero, already unimaginably cold, already far colder than anything in nature. But even that was not cold enough. Scientists found ways to slip beneath the Doppler limit, using techniques with names that carry a quiet poetry. One is called Sisyphus cooling, named after the figure from old stories who pushed a stone endlessly uphill. In this method, atoms are made to climb tiny hills of light energy over and over, losing a little kinetic energy each time they reach the top, only to find themselves at the bottom of another hill, climbing again, always climbing, always slowing. It is a gentle trap, and it works, pushing atoms to temperatures even lower than the Doppler limit allows. Colder and colder, until something remarkable happens. When atoms are cooled to within billionths of a degree of absolute zero, they stop behaving like separate things. Their quantum waves, normally too small to notice, begin to stretch and overlap, and the atoms lose their individuality. Thousands of them, sometimes hundreds of thousands, begin to move as one, to occupy the same quantum state, to act not as a crowd of particles, but as a single entity spread across space. This is called a Bose-Einstein condensate, predicted decades before it was ever made. Imagined first in the mathematics of Satyendra-Nath Bose and Albert Einstein in the 1920s, a state of matter that exists only in the deepest cold, where the boundaries between atoms dissolve and the quantum world becomes visible at a scale you could almost see with your eyes. It took 70 years to make one. In 1995, Eric Cornell and Carl Wyman, working in a laboratory in Colorado, cooled a small cloud of rubidium atoms to just a few billionths of a degree above absolute zero, and watched as the atoms fell into the same quantum state, one by one, then all at once, like a whisper becoming a single voice. It was the coldest thing that had ever existed, colder than any corner of space, colder than the Boomerang Nebula, colder than the void between galaxy clusters, a tiny cloud of atoms, no bigger than a grain of sand, holding a temperature closer to absolute zero than anything nature had ever produced. And now, there is a small device aboard the International Space Station called the Cold Atom Laboratory, where this work continues in a place that offers something no Earthbound lab can provide: the near absence of gravity. On Earth, when you release a cloud of ultra-cold atoms, gravity pulls them down, and within a fraction of a second, they fall out of the trap and warm up. The observation window is brief, a heartbeat of data before the cold is lost. But in microgravity, the atoms float. They do not fall. They linger in their condensate state for much longer, seconds stretching into what feels like stillness, giving scientists time to watch, to measure, to listen to what the quantum world is saying when it is this quiet. There are other kinds of condensates too. Fermions, the particles that make up most of ordinary matter, electrons, protons, neutrons, do not naturally fall into the same quantum state the way bosons do. They are governed by a different rule, one that insists each particle remain distinct, but at ultra-low temperatures, fermions can pair up, 2 by 2, and these pairs behave like bosons, slipping together into a shared quantum state. These are called fermionic condensates, and they are harder to make, rarer, more delicate. But they exist, another quiet wonder found only at the edge of absolute zero. And there is superfluidity. When helium-4 is cooled to just a couple of degrees above absolute zero, it undergoes a transformation that seems to belong more to a dream than to physics. It becomes a superfluid, a liquid that flows with no viscosity at all, no friction, no resistance, no loss of energy as it moves. A superfluid does not behave the way any ordinary liquid does. If you set it spinning in a cup, it will spin forever, never slowing down, never stopping. If you place it in a container, it will creep up the walls, a thin film climbing silently over the rim, flowing down the outside, as though the container simply cannot hold it. It can pass through pores so small that no ordinary liquid could fit, slipping through gaps only atoms wide, without effort, without sound. It is one of the strangest things that cold can do, turning a familiar substance into something that defies every intuition about how liquids should behave. And yet it is real, observed, measured, a quiet rebellion against friction itself, happening in laboratories, in cryostats humming softly in the dark. All of this, the condensates, the superfluids, the atoms slowed to nearly nothing by light, all of it lives in a narrow sliver of temperature just above absolute zero, a place the universe does not naturally go, a place that must be made carefully, patiently, one layer of warmth removed at a time. And perhaps that is what makes it so remarkable, not the cold itself, but what the cold reveals, that beneath the warmth and motion of everyday things, there is a deeper order, a quieter world, where particles move as one, where liquids forget how to stop, where the rules we take for granted gently fall away. You do not need to understand all of it tonight. You only need to know that it is there, waiting, in the stillness beneath the motion, in the silence beneath the sound, the same stillness that is settling over you now as the night deepens and the world outside grows quiet, and the cold, patient and vast, holds everything gently in place. And there is another quiet miracle that lives in the cold. Something that happens when certain materials are cooled far enough, when the last traces of warmth are drawn away and resistance itself simply vanishes. This is superconductivity, the complete absence of electrical resistance, A current set flowing in a superconducting loop will continue, not for a long time, not for centuries, but in principle, forever, with no energy lost, no friction, no fade, just a current circling endlessly in perfect silence. It was first discovered in 1911 by a Dutch physicist named Heike Kamerlingh Onnes. He had been working with liquid helium, learning to cool things to temperatures no one had reached before. And when he cooled a thread of mercury down to about 4.2 Kelvin, something unexpected happened. The electrical resistance, which had been falling gradually as the mercury grew colder, did not just keep falling, it dropped, all at once, to nothing. Not nearly nothing, not approximately nothing. Nothing. As if the mercury had forgotten how to resist, as if the cold had unlocked a hidden doorway in the metal, and the current simply walked through. Onnes could hardly believe his own measurements. He repeated the experiment, checked his instruments, and found the same result each time. Below a certain temperature, mercury became a perfect conductor, a material with no resistance at all. That was more than a century ago, and since then, superconductivity has been found in many other materials. Some require temperatures just a few degrees above absolute zero. Others, called high-temperature superconductors, work at relatively warmer conditions, though warmer here still means far below freezing, far below the coldest winter night, far below anything you would ever feel on the surface of the Earth. The word high is generous. It simply means not quite as impossibly cold as before. But even at those temperatures, the effect is the same. Resistance disappears, and current flows without loss, as though the material has entered a kind of dream where the ordinary rules of electricity no longer apply. This is not just a curiosity locked away in laboratories. Superconducting magnets are at work in hospitals right now, tonight, in MRI machines, the ones that create detailed images of the human body without surgery, without radiation. The magnets inside those machines are cooled by liquid helium, kept at temperatures cold enough for superconductivity to take hold. And because the current flows without resistance, the magnets can generate powerful, stable fields, strong enough to align the tiny magnetic moments of atoms inside living tissue and listen to the faint signals they return. All of that because of the cold. And beneath the border between France and Switzerland, there is a tunnel, a ring, 27 kilometers around, where particles are accelerated to nearly the speed of light. The Large Hadron Collider, one of the most ambitious instruments ever built. And to guide those particles along their circular path, the collider uses magnets, enormous superconducting magnets, cooled by 96 tons of superfluid helium to a temperature of 1.9 Kelvin. Colder than outer space. One of the coldest large-scale places on Earth, not found in nature, but made, deliberately, so that particles smaller than atoms can be steered with exquisite precision around a ring buried underground. And there are places colder still. Inside the processors of certain quantum computers, temperatures drop to about 15 millikelvin, 15 thousandths of a degree above absolute zero. A cold so deep, it is difficult to express in ordinary terms. At those temperatures, the quantum bits at the heart of the machine can maintain their delicate states long enough to perform calculations. Because warmth, even the faintest trace of it, is noise, vibration, disruption, and quantum information is fragile. It exists in superpositions, in entanglements, in states that collapse at the slightest disturbance. The cold does not make the computation happen, but it makes the silence in which computation becomes possible. A silence so complete that even a single stray photon would be too loud. All of this, the superconductors, the colliders, the quantum machines, all of it reaching toward the same place, toward the stillness at the bottom of the temperature scale, where the ordinary noise of the world falls away, and something deeper can be heard. And now, let us go further. Not deeper into the cold of laboratories, but outward, into the cold of the universe itself, to a light that has been traveling for longer than anything else you will ever encounter. The cosmic microwave background. It fills all of space, every direction you could look, every corner of the sky, a faint glow, invisible to the eye, but detectable by instruments tuned to the right frequency. It is the oldest light in the universe, released about 380,000 years after the Big Bang, when the cosmos had cooled just enough for atoms to form for the first time. Before that moment, the universe was a fog, a dense, opaque sea of plasma, so hot that electrons could not settle into orbit around nuclei. Light could not travel freely. Every photon was scattered almost immediately, absorbed and re-emitted, trapped in an endless maze of charged particles. The universe was bright, unimaginably bright, but nothing could see through it. It was like being inside a star, in every direction, with no edge, no outside, no darkness anywhere. And then, slowly, the temperature dropped. The plasma cooled. Electrons found their way to protons and held on. Atoms formed. Hydrogen, helium, the simplest elements. And as the charged particles became neutral atoms, the fog cleared. Light was released, free to travel at last, streaming outward in every direction, carrying with it a portrait of the universe as it was in that moment of clearing. That light has been traveling ever since, for 13.8 billion years, stretched by the expansion of space, cooled from the fierce glow of a young universe to a faint whisper at 2.725 Kelvin. Just a breath above absolute zero, a lullaby, still echoing. And it is remarkably uniform, almost the same temperature everywhere, in every direction. From every part of the sky, the cosmic microwave background varies by only about 1 part in 100,000, a smoothness so perfect it seems almost impossible. But those tiny variations, those faint ripples in the temperature, are not imperfections. They are seeds. Each slightly warmer or cooler patch in the ancient light corresponds to a region where matter was just a little more or less dense than its surroundings. And over billions of years, gravity took hold of those small differences, pulling matter together where it was slightly denser, letting it drift apart where it was slightly thinner. And from those whisper-thin variations, everything grew. Every galaxy, every cluster of galaxies, every vast web of light stretching across the cosmos, all of it traced back to those almost imperceptible ripples in the oldest light there is. The seeds of everything you have ever seen in the night sky, planted in a glow that is now barely warmer than nothing at all. And that light is still here, still arriving, still washing over the earth tonight, passing through walls, through the air, through you, unnoticed, unfelt. A remnant of the first clearing, the first moment the universe became transparent, the first time light could simply go. It asks nothing of you. It carries no urgency. It has been patient for nearly 14 billion years, and it will go on long after every star has dimmed. For now, it is enough to know it is there, everywhere, a quiet warmth in the cold, a memory the universe still carries, softly, gently, like a breath held since the beginning of time. That moment, when the universe first became clear, has a name. Scientists call it recombination, which is a curious word because atoms were not recombining at all. They were combining for the very first time. Protons and electrons finding each other, settling into partnership, forming hydrogen, forming helium, and in doing so, releasing their grip on light. It was the first time photons could travel freely, and that ancient light is what we now call the cosmic microwave background. It was not understood all at once. It took decades of careful listening. Patient instruments pointed at the sky, gathering signals so faint they could easily be mistaken for noise. The first satellite to map this ancient glow was called COBE, launched in 1989, and it confirmed what many had hoped, that the cosmic microwave background was almost perfectly uniform, but not quite. There were tiny differences, variations so small they had been invisible until then. A few years later, another satellite called WMAP looked more closely with sharper eyes and revealed those variations in finer detail. showing the patterns that would one day become galaxies, become clusters, become the architecture of everything. And then came Planck. The Planck satellite, launched in 2009, measured the temperature of the cosmic microwave background with a precision of a few millionths of a degree. A few millionths. Imagine holding a thermometer so sensitive it could detect the difference between one breath and the next from across a room. That is the kind of stillness required to read the oldest light in the universe. And what Planck found was a map, a portrait of the cosmos, as it was nearly 14 billion years ago, painted in the softest variations of warmth and cold. Most of those variations are well understood. They match the predictions of our best models, the expected fingerprints of a young universe settling into structure. But not all of them. There is one cold spot, larger than expected, a region in the southern sky where the temperature dips just slightly more than it should. It has puzzled cosmologists for years. Some have suggested it corresponds to a supervoid, an enormous region of space with very few galaxies, where the relative emptiness leaves a cold imprint on the passing light. And that idea may be part of the answer. Cold spots in the CMB do seem to align with supervoids in the large-scale structure of the universe, places where matter is sparse and the fabric of space stretches a little more freely. But this particular cold spot, the large one, remains not fully explained. It sits quietly in the data, a small mystery the universe has not yet given up. And the cosmic microwave background holds other secrets too, not just in its stillness, but in the way it changes when it passes through something. When CMB photons travel through the hot gas inside a galaxy cluster, they can gain a small amount of energy. They enter the cluster cold and ancient and emerge just slightly warmer, just slightly shifted. This is called the Sunyaev-Zeldovich effect, and it leaves a faint imprint, a subtle shadow or brightening in the microwave background. It is so delicate that for years it was beyond the reach of our instruments. But now, astronomers use this effect to detect galaxy clusters, not by their own light, but by the mark they leave on the oldest light there is. The clusters reveal themselves, not by shining, but by gently altering something that was already passing through. There is another pattern in the CMB, a broader one, a kind of lopsidedness in the temperature across the whole sky. One side of the sky appears very slightly warmer, the other very slightly cooler. This is called the dipole anisotropy, and it tells us something remarkable. It tells us that our galaxy, our entire local group of galaxies, is moving, drifting through space at about 600 kilometers per second, relative to the cosmic microwave background itself. We are not still. We have never been still. The ground beneath you feels solid. The night feels calm. But you are being carried at tremendous speed through a universe that remembers where everything began. The CMB is the closest thing we have to a universal frame of reference, and against it, we are gently, quietly, in motion. Now, when we speak of cold in space, it is worth pausing to consider what temperature even means out there. Because the vacuum of space, the emptiness between worlds, does not truly have a temperature. Temperature belongs to things, to matter, to radiation, to objects that can absorb and emit energy. The vacuum itself is just absence, a stage with no performers. If you placed a thermometer in the void between stars, it would not read the temperature of space. It would read its own temperature, slowly adjusting, radiating its heat away into the dark, approaching, but never quite reaching, the faint warmth of the cosmic background. And this is why temperature in space can be so deceptive, so full of extremes that exist side by side. An object in direct sunlight near Earth, a satellite panel, a spacesuit glove turned toward the sun, can reach over 120 degrees Celsius, hot enough to burn. But turn that same object away from the sun, let it face the dark, and its temperature drops far below freezing. The difference between one side and the other can be hundreds of degrees, separated by nothing more than the angle of light. Spacecraft must manage these extremes constantly. Their sunlit surfaces bake, while their shadowed surfaces freeze. Engineers design elaborate thermal systems, reflective coatings, radiators, heaters tucked into the coldest corners, all to keep instruments within the narrow range where they can function. It is one of the quieter challenges of space travel, not the drama of launch or landing, but the slow, persistent negotiation with heat and cold that never stops. And some instruments, the most sensitive ones, need to be kept extraordinarily cold. The James Webb Space Telescope, orbiting far from Earth, operates at about 40 Kelvin, 40 degrees above absolute zero. To achieve this, it carries a sunshield the size of a tennis court, 5 thin layers of specially coated material, each one blocking a little more of the sun's warmth. On the sunward side, temperatures climb above 80 degrees Celsius. On the other side, behind that shield, the telescope sits in a cold so deep that its mirrors and instruments can detect the faintest infrared whispers from the earliest galaxies, light that has been traveling for over 13 billion years, stretched and cooled by the expansion of the universe, arriving as warmth so faint that any stray heat from the telescope itself would drown it out. And so the telescope must be cold, profoundly cold. Not because cold is the goal, but because cold is the condition for listening. The quieter the instrument, the more it can hear. The colder the mirror, the deeper it can see. It is a kind of patience built into metal and glass, a willingness to become almost as cold as the universe itself in order to receive what the universe has been sending for so very long. And tonight, that telescope is out there, turning its cold eye toward the dark, gathering light that left its source before the Earth existed, before the sun ignited, before the Milky Way had taken its familiar shape, all of it arriving now, faintly, gently, into an instrument that has made itself quiet enough to notice. And it is not the only instrument to have embraced this quiet discipline. Before the Webb telescope, there was another, the Herschel Space Observatory, which carried the largest mirror ever launched into space, a single piece of silicon carbide stretching 3.5 meters across. Herschel was designed to see in the far infrared wavelengths even longer and fainter than those the Webb pursues. And to do this, its detectors had to be cooled to near absolute zero, just fractions of a degree above the coldest anything can ever be. Because that is the rule of infrared astronomy. The detector must be colder than the thing it is trying to see, any warmth at all. Even the faintest thermal hum from the instrument itself would wash over the signal like a bright light flooding a room where you were trying to watch a single candle flicker in the distance. The colder the detector, the more invisible it becomes to itself, and the more clearly it can perceive what lies beyond. Herschel carried a tank of superfluid helium to maintain that extraordinary cold, over 2,000 liters of it, slowly boiling away into space, molecule by molecule, keeping the instruments in a state of deep stillness. But cryogenic coolant does not last forever. It cannot be refilled. It cannot be replenished. And so, from the moment Herschel opened its eye, a clock was ticking. The helium was always leaving. And one day, it would be gone. That day came in April of 2013. The last of the helium evaporated. The detectors began to warm, and Herschel's vision slowly faded. Not because anything broke, not because of any failure, but because the cold ran out. The observatory had simply used up its ability to be quiet. There is something gently poignant about that. A telescope that could only see for as long as it could stay cold. Its lifetime measured not in years of wear, but in liters of vanishing helium. And when the cold was gone, the mission was over. The universe was still sending its signals, but Herschel could no longer hear them. This is the cost of listening to the cold universe. You must become part of it, and that is not easy to sustain. But cold is not only a condition for seeing, it is also a condition for becoming, for making worlds that are strange and beautiful in ways that warmth could never allow. Consider Titan, the largest moon of Saturn, a world wrapped in a thick golden haze, with a surface temperature of about 94 Kelvin, nearly 180 degrees below 0 Celsius. At that temperature, water is hard as granite. It forms the bedrock, the mountains, the frozen ground beneath your feet. But methane, which on Earth is a gas you might find rising from a marsh, on Titan, methane is a liquid. It rains there. Methane falls from thick orange clouds, gathers into streams, carves channels through the icy terrain, and flows downhill into rivers that wind across the surface. Those rivers empty into lakes, and those lakes gather into seas. Vast, dark bodies of liquid methane and ethane, sitting quietly under a sky that never clears. It is a landscape shaped entirely by cryogenic chemistry, a world where the familiar cycle of rain and rivers and seas plays out, but with different molecules, at temperatures so cold that the chemistry of life as we know it could not function. And yet the cycle itself is there, recognizable, almost familiar, as if cold had simply rewritten the same story in a different language. Closer to Jupiter, another kind of cold world holds a different secret. Europa, one of the 4 great moons that Galileo first saw through his telescope, has a surface temperature of about 110 Kelvin. Its face is covered in ice, cracked and ridged and streaked with faint reddish lines. It looks frozen through and through, but beneath that shell of ice, there is almost certainly an ocean, a real ocean, of liquid water, kept warm not by sunlight, but by the constant flexing of the moon's interior as Jupiter's gravity kneads it like dough. The surface is bitterly cold, but somewhere below, perhaps 15 or 20 kilometers down, the water is warm enough to flow. Warm enough, perhaps, for chemistry to happen in ways we have not yet imagined. And then there is Enceladus, a small moon of Saturn, barely 500 kilometers across. Its surface is coated in fresh ice so white and so smooth that it reflects nearly all the sunlight that touches it. This makes Enceladus one of the brightest objects in the solar system, and also one of the coldest, because almost no solar energy is absorbed. But Enceladus is not still. Along its south pole, great cracks in the ice, sometimes called tiger stripes, open into the darkness below. And from those cracks, geysers erupt, plumes of water, ice, and vapor, shooting hundreds of kilometers into space, fed by a subsurface ocean that has no business existing on a world so small and so far from the sun. And yet it does. Warm water beneath cold ice, venting into the vacuum, carrying with it traces of salt and silica and simple organic molecules. Cold on the outside, something else entirely within. Even Mars, our closest neighbor that we think of as merely chilly, knows a deeper cold than most people expect. At the Martian poles, winter brings temperatures low enough to freeze not just water, but the very atmosphere. Carbon dioxide, the gas that makes up most of the thin Martian air, falls out of the sky as frost and ice, settling onto the surface in great white sheets of dry ice. The polar caps grow, spreading across the landscape, as the atmosphere itself slowly thins, some of it now lying frozen on the ground. This is a cycle unlike anything on Earth, an entire world where winter means the air turns to ice. And the polar night on Mars can last for months. The sun dips below the horizon and does not return. The surface is plunged into a prolonged and deepening cold, with no warmth, no light, just the slow accumulation of frozen carbon dioxide under a black and starless sky. Then, gradually, the seasons turn. The sun creeps back. The dry ice begins to sublimate, rising directly from solid back to gas, and the atmosphere slowly reinflates. The caps retreat, the air thickens, and Mars breathes again. It is a rhythm, patient and ancient, playing out over Martian years that are nearly twice as long as our own. A world exhaling its atmosphere onto the ground each winter and inhaling it back each spring. All of these places, Titan with its methane rain, Europa with its hidden ocean, Enceladus with its quiet geysers, Mars with its breathing poles, they are all cold, profoundly cold by any human measure, and yet none of them are still. None of them are empty. The cold has not stopped anything. It has only changed the terms. Different chemistries, different rhythms, different kinds of motion, all unfolding in temperatures that would end most familiar processes in an instant. But the universe does not require warmth to be interesting. It only requires energy, in whatever form, moving in whatever way the cold allows. And so these worlds turn quietly in the outer dark, each one carrying its own version of activity, its own slow story, written in ice and methane and frozen air. And there are others, turning in that same outer dark, closer to Jupiter's enormous pole. Ganymede, the largest moon in the entire solar system, larger even than the planet Mercury, drifts through Jupiter's shadow with surface temperatures that range from about 70 Kelvin in its coldest regions to roughly 150 Kelvin, where sunlight touches the ground. It is a world of ancient grooved terrain, long parallel ridges carved into ice billions of years ago by forces we still do not fully understand. At 70 Kelvin, the ice on Ganymede is harder than most rock on Earth. It does not crack easily. It does not flow. It simply endures, holding the memory of whatever shaped it so long ago. Nearby, Callisto orbits in a wider, slower path. Its surface is among the most heavily cratered in the solar system, a face that has barely changed in 4 billion years. Temperatures there range from about 80 to 165 Kelvin, and the cold has preserved that battered landscape almost perfectly. Every impact scar remains, every ring and ridge, as though time itself slowed down in the deep chill and simply forgot to erase anything. Callisto is a kind of archive, a record of the early solar system written in ice and stone and kept frozen in place. But even these cold Jovian moons are warm compared to what lies further out. Beyond the orbit of Neptune, far past the last of the giant planets, there is a vast and quiet region called the Kuiper Belt. It stretches across billions of kilometers, a wide band of icy bodies drifting in temperatures of roughly 30 to 50 Kelvin, thousands of them, perhaps hundreds of thousands. Small frozen worlds made of water, ice, and methane and ammonia and compounds that have no name in everyday language. They move slowly out there, their orbits so large that a single trip around the sun can take centuries. Some are round enough to be called dwarf planets. Others are irregular, tumbling fragments left over from the formation of the solar system, never gathered into anything larger, never warmed by anything close. The light from the sun still reaches them, but only barely. A faint point of light, brighter than any star in the sky, but no longer warm, no longer able to melt or move or change anything on those distant surfaces. The Kuiper Belt is a place where the sun's influence is fading, where its gravity still holds, but its warmth has all but disappeared. And then, even further, there is Sedna, one of the most distant known objects in the solar system. Sedna follows an orbit so elongated that it takes roughly 11,000 years to complete a single loop around the sun. At its closest approach, it is still far beyond the Kuiper Belt, and at its furthest point, it's a aphelion. It drifts to a distance so great that the sun is just another star in a crowded sky. Out there, Sedna's surface temperature drops to about 12 Kelvin, 12 degrees above absolute zero, colder than most of interstellar space. A small reddish world, alone in the dark, carrying its thin coat of frozen methane and nitrogen across an orbit that most of the universe will never notice. No one knows exactly how Sedna got there. Its orbit does not fit neatly into the models we have for how the solar system formed. Something placed it on that long, lonely path. Perhaps a passing star billions of years ago. Perhaps the gravity of a planet we have not yet found. Whatever the cause, Sedna is out there now, patient and cold, circling a sun it can barely see. And beyond Sedna, beyond the farthest reach of our solar system, the temperature of space itself settles to something close to the cosmic microwave background, roughly 2.7 Kelvin, that faint warmth left over from the beginning of everything. The afterglow of the Big Bang is all that remains between the stars. Interstellar space is not truly empty, but it is profoundly cold and profoundly still. And yet, even in that stillness, there are wanderers, rogue planets, worlds that were once part of star systems like our own, ejected by gravitational encounters with larger planets or passing stars, flung outward into the space between suns. They drift through the galaxy with no star to orbit, no light to warm them, slowly cooling over billions of years as whatever heat they carried from their formation radiates away into the dark. Some of them may be gas giants, others rocky, others icy, There may be billions of them in our galaxy alone, outnumbering the stars. A vast, unseen population of orphaned worlds, each one a little colder than the last, each one a little closer to the temperature of the void around it. And some of them, as far as we can tell, may not be entirely frozen inside, deep beneath the surface of a rogue planet, shielded from the cold of space by hundreds of kilometers of rock and ice. Radioactive elements may still be decaying, slowly, steadily, releasing just enough heat to keep a thin layer of water liquid, a subsurface ocean, with no sunlight, no star, no sky, just warmth from within, held in place by the quiet energy of atoms falling apart. It is a strange thought, an ocean that has never seen a photon, warmed by nothing but the slow unraveling of matter itself. We do not know if such oceans exist for certain, but the physics allows it, and the universe tends to fill whatever possibilities the physics allows. There are other objects drifting through the cold that are not quite planets and not quite stars. Brown dwarfs, sometimes called failed stars, too massive to be planets, but too small to sustain the hydrogen fusion that powers a true star. They form the same way stars do, from the collapse of gas and dust. But they never gather enough mass to ignite that sustained nuclear fire. Instead, they glow faintly with the heat of their formation, and then they cool, slowly, over billions of years. The coldest known brown dwarf is called WISE 0855, a dim object discovered by a space telescope surveying the sky in infrared light. Its surface temperature is estimated at about 250 Kelvin, roughly minus 23 degrees Celsius, about as cold as a winter night in the Arctic. A star that never was, now cooler than many places on Earth, drifting through the galaxy with a faint warmth that only the most sensitive instruments can detect. It is a humbling object, a reminder that the boundary between star and planet is not sharp, that the universe produces a whole spectrum of things that burn, and things that merely glow, and things that simply cool in silence. And then there are the ice giants, Uranus and Neptune, worlds we have visited only once, briefly, with the Voyager spacecraft decades ago. They are cold on the outside, but inside, deep inside, something remarkable may be happening. Under the enormous pressure of their thick atmospheres, water behaves in ways it never could on Earth. It may exist in a phase called superionic ice, where the oxygen atoms lock into a rigid crystal lattice, frozen in place, while the hydrogen atoms flow freely through that lattice like a liquid. It is ice and fluid at the same time, a state of matter that exists nowhere on our planet, born only under pressures millions of times greater than the air we breathe. And deeper still, carbon atoms, squeezed by that same crushing pressure, may be compressed into crystal form. Diamond, raining slowly through the thick inner layers of these giant worlds, falling like quiet stones through an ocean of exotic ice. It is not the kind of rain anyone would recognize. There is no sky, no clouds in any familiar sense, just immense pressure and cold and chemistry doing what chemistry does when the conditions demand it. Carbon becoming crystal, sinking toward the core, accumulating over millions of years in a place no instrument has ever reached. The cold does not stop the universe from being extraordinary. It only asks it to be extraordinary in different ways. Beyond the ice giants, beyond the outermost worlds of any star system, lies the space between the stars themselves, the interstellar medium, a vast and quiet territory that fills the galaxy like a slow, cold breath. It is not uniform. It is not the same everywhere. Some of it is warm, heated by the light of nearby stars or the violence of ancient explosions. But much of it is cold, regions of neutral hydrogen gas, drifting at temperatures of about 80 Kelvin, nearly 200 degrees below freezing. These stretches are known simply as the cold neutral medium, and they span distances so large that light itself takes years to cross them. This cold gas is not dramatic. It does not glow. It does not announce itself. It simply exists, filling the spaces between stars with a quiet, steady presence, like fog settled into a valley that has no edges. But the cold neutral medium is not left entirely undisturbed. When a massive star reaches the end of its life, it dies in a supernova. An explosion so powerful, it briefly outshines an entire galaxy. And the shockwave from that explosion rushes outward, slamming into the cold gas around it, pushing it aside, heating it, carving an enormous cavity in the interstellar medium, a bubble of hot, thin gas where the cold once was. These bubbles can stretch for hundreds of light years, hollowed out regions where the gas is sparse and warm, surrounded on all sides by the denser cold that was swept away. Our own solar system sits inside one of these cavities. It is called the local bubble, a region of hot, low-density gas roughly 1,000 light-years across, carved by a series of supernova explosions that occurred millions of years ago, long before anything resembling human life existed on Earth. Stars that no longer exist, stars that burned through their fuel and detonated, shaped the very neighborhood we now call home. We live inside the aftermath of their deaths, surrounded by the thin, warm remnant of their final moments. And beyond the walls of this bubble, the cold, neutral medium continues, undisturbed, patient, as it has been for a very long time. Through all of this, through the cold gas and the warm bubbles and the vast emptiness between galaxies, particles are moving, cosmic rays, fragments of atoms, protons, and atomic nuclei stripped of their electrons, traveling at nearly the speed of light. They pass through the coldest regions of space without slowing, without stopping, carrying energies that dwarf anything we produce on Earth. Yet they are invisible, silent, threading through the cold like needles through still water. They do not feel the temperature around them. They're too fast, too energetic. They belong to a different story, one written in violence and acceleration. But they travel through the same quiet spaces, the same cold corridors between the stars, and in that way, they are part of this story too. Now, closer to where stars are being born, the cold takes on a different role. Around young stars, in the earliest stages of a solar system's life, there are disks of gas and dust, protoplanetary disks, swirling slowly around a newborn sun. Near the star, the disk is warm, heated by the light of the young sun at its center. But farther out, in the outer reaches of the disk, temperatures fall, 10 Kelvin, perhaps even less, colder than most of interstellar space. And it is there, in that deep cold, that something important begins. Dust grains coated in thin mantles of ice begin to stick together, slowly, gently, building larger and larger clumps. These are the icy planetesimals, the first solid bodies in a young solar system, and they will go on to become many things. Some will become comets, drifting in long, slow orbits for billions of years, carrying their ancient ice like a memory of the place where they were made. Others will become the cores of giant planets, accumulating so much frozen material that they grow massive enough to pull in gas from the surrounding disk, becoming worlds of immense size. There is a boundary in every protoplanetary disk, a distance from the central star where the temperature drops just low enough for water to freeze into solid ice. It is called the snow line, and it is one of the most important thresholds in the formation of a solar system. Inside the snow line, water remains vapor, and the solid material available to build planets is limited to rock and metal. But beyond it, ice becomes abundant, and the amount of solid material available increases dramatically. This is why the gas giants of our own solar system, Jupiter, Saturn, Uranus, Neptune, all formed in the outer regions, beyond the snow line, where the cold gave them what the warmth could not, enough frozen material to grow into something enormous. The cold does not prevent creation. It enables a particular kind of it, patient and slow and built from ice. And on some of the worlds that formed in this cold, the ice does not simply sit still. On Triton, the largest moon of Neptune, there are smooth, resurfaced plains that suggest something once flowed across the surface. Not lava, not molten rock, but cold materials, water, ammonia, methane, erupting from below and spreading across the frozen ground before hardening again. This is cryovolcanism, volcanic activity defined not by heat, but by cold. eruptions of ice instead of fire, reshaping a world's surface in slow, frigid waves. Triton's plains are eerily smooth in places, as though something wiped the old terrain away and laid down a fresh layer. And the best explanation we have is that it did. Icy flows, rising from within, covering the ancient craters and scars, leaving behind a landscape that looks almost new. Pluto may tell a similar story. Among its mountains and frozen nitrogen plains, there is a feature called Right Mons, a broad, tall mountain with a central depression at its summit. It resembles a volcanic structure, but one built not from basalt or magite, from ice. If it is a cryovolcano, and there is reason to believe it may be, then Pluto too has been shaped by eruptions of cold material, a world so far from the sun that its volcanoes erupt with the very substances that would be liquid or gas on Earth. Cold worlds are not dead worlds. They simply express themselves differently. And farther still, beyond Pluto, beyond the Kuiper Belt, beyond the faintest influence of the sun, two small spacecraft are drifting. Voyager 1 and Voyager 2, launched in 1977, have crossed the boundary of the solar system and entered interstellar space. They are now surrounded by the cold medium between the stars, experiencing temperatures close to the cosmic microwave background, just a few degrees above absolute zero. They carry no warmth from home, only the faint heat of their decaying plutonium power sources, which grow weaker with each passing year. Slowly, quietly, they are becoming part of the cold they travel through. No human hand will ever touch them again. No human eye will ever see them. They will drift for millions of years, perhaps billions, through the same cold corridors where cosmic rays fly and neutral hydrogen hangs in stillness, carrying a golden record etched with sounds and images from a small, warm world. They are the farthest things we have ever sent into the cold, and they are still going, still moving, still cooling, still carrying a message from a species that looked up at the dark and the cold and chose to send something into it anyway. The cold of interstellar space does not care about messages. It does not receive or reject. It simply is, vast and patient and everywhere, the default state of almost everything that exists. And yet, through it, two small machines are traveling, growing colder with every passing moment, but not yet silent, not yet still. Voyager 1, the farther of the two, is now the most distant human-made object in existence. More than 24 billion kilometers from the sun, a distance so vast that its radio signals traveling at the speed of light take nearly a full day to reach us. It is out there now, in the cold between stars, a small metal body no larger than a compact car, drifting through a darkness that stretches in every direction without end. But the Voyagers were not the first to travel so far from home. Before them came the Pioneer spacecraft. Pioneer 10 and Pioneer 11 launched in the early 1970s. They too sailed past the giant planets and out toward the edge of the solar system. And as they traveled, something strange happened. Something so small it took years to notice. The Pioneer spacecraft were slowing down. Not by much. The deceleration was tiny, barely measurable. Just a whisper of force pressing back against their motion. For decades, it puzzled engineers and physicists. Some wondered if it hinted at new physics, a flaw in our understanding of gravity, or some unseen property of space itself. But the answer, when it finally came, was far more gentle than that. It was heat. The spacecraft were warm, warmer than the space around them. Their electronics, their power sources, their instruments, all produced small amounts of thermal energy, and that heat radiated outward in every direction, but not quite evenly. A little more warmth escaped from one side than the other, and that imbalance, that faint asymmetry of radiated light, created a force so small it would take billions of years to stop a falling leaf, but in the frictionless silence of deep space, over years and decades, it was enough to slow a spacecraft down. Thermal radiation, pressing against the cold. That was all it was. And yet, it took some of the finest minds in physics more than 30 years to be certain. This is one of the quiet truths about the cold of space. Heat does not leave an object easily out there. On Earth, warmth escapes in many ways. It flows through contact, metal to skin, stone to bare feet. It rises on currents of air, carried upward by convection, spiraling away from a candle flame or a warm road in summer. But in the vacuum of space, there is no air. There is no surface to touch. There is nothing to carry heat away. The only path left is radiation. An object in space can only cool by emitting light. Infrared light mostly, invisible to our eyes, but real. Each photon that leaves carries a tiny amount of energy with it, and slowly, very slowly, the object grows cooler. This is why cooling in space takes so long. A warm object placed in the void would hold its heat for a surprisingly long time, not because space is warm, but because there is no medium to pull the warmth away, only the slow, patient release of photon after photon, each one carrying the smallest possible parcel of energy into the dark. It is a kind of loneliness, if you allow the metaphor, heat with nowhere to go, radiating into a silence that offers nothing in return. Far from the sun, in the cold outer reaches of the solar system, there are objects that have been cooling this way for billions of years. Asteroids, ancient and dark, drifting through the space beyond Jupiter and Saturn. Their surfaces are coated in dark organic compounds and frozen volatiles, ices that have not melted since the earliest days of the solar system. They are among the oldest unchanged objects we know of, relics of a time before the Earth existed, before the sun had fully settled into its steady burning. And even these cold, dark, ancient bodies are shaped by the faintest warmth they carry. As an asteroid rotates, one side faces the distant sun and absorbs a small amount of light. That side warms, just barely. And as the asteroid turns, the warmed surface rotates away from the sun and begins to radiate its heat back into space. But by the time it radiates, it is no longer facing the sun. It is facing a different direction. And so the tiny push of that radiated heat does not point straight back toward the sun. It pushes at an angle. This is called the Yarkovsky effect. A force so small it seems impossible that it could matter, and yet, over millions of years, it does. It can shift an asteroid's orbit, nudge it inward toward the sun, or outward into deeper cold, slowly, imperceptibly, one radiated photon at a time. The cold of space is not passive. It interacts with everything that carries even the faintest warmth, and over long enough timescales, it reshapes the paths of worlds. But there is something colder still, something we have never touched, never seen, never directly measured. Beneath the faint glow of the cosmic microwave background, beneath that quiet hum of warmth left over from the beginning of everything, there is another relic, even older, even colder. The cosmic neutrino background. Its predicted temperature is about 1.95 Kelvin, colder than the cosmic microwave background, colder than the space between galaxies, colder than almost anything we have a name for. These neutrinos were born in the first second after the Big Bang, a time when the universe was so hot and so dense that even these ghostly particles were bound up in the chaos, colliding and scattering with everything around them. But as the universe expanded and cooled, the neutrinos broke free. They stopped interacting with matter almost entirely, and they have been traveling ever since, cooling as the universe stretched around them, growing colder with every passing age. They are everywhere. Trillions of them pass through your body every second, through the walls, through the earth itself, without touching a single atom. They are the most elusive remnants of the early universe, and they carry information from a moment so ancient that even the cosmic microwave background cannot reach it. If we could detect them, if we could build an instrument sensitive enough to catch these faintest of all messengers, we would have a window into the universe as it was just 1 second after the beginning, a portrait of creation painted in the coldest possible light. But for now, they remain invisible, passing through everything, touching nothing. A sea of almost zero warmth filling all of space, unnoticed and unmeasured. They are perhaps the loneliest cold there is. And this, all of this, is part of a single long story. The temperature of the universe has been falling since the moment it began. In the first fractions of a second, temperatures were so high that no atoms could exist. No particles as we know them could hold together. The universe was a blinding fire with no form and no structure. Then it cooled, and particles formed. Then it cooled further, and atoms appeared. Then further still, and stars ignited, galaxies gathered, planets condensed from rings of dust and ice. Every structure we see in the night sky, every star, every nebula, every frozen moon, exists because the universe cooled enough to allow it. And the cooling has never stopped. It continues now, tonight, as the universe expands and the distances between galaxies grow wider, as the cosmic microwave background stretches into longer and longer wavelengths, losing energy so gradually that no instrument on Earth could measure the change from one year to the next. The universe is growing colder, and it will continue to do so, indefinitely. There is no mechanism to reverse it, no force that will gather the heat back together. The expansion carries everything apart, and the temperature falls, and falls, and falls. Not quickly, not dramatically, just a slow, quiet, endless descent. Like a breath that never quite finishes leaving, and so the breath continues, carrying warmth away, slowly, so slowly that the change is almost nothing at all. But given enough time, even almost nothing becomes everything. In about 100 trillion years, every star in the universe will have burned through its fuel. The last red dwarfs, those small and patient stars that sip their hydrogen so carefully, will finally flicker and dim and go dark, one by one. Then all at once, the sky will empty of light. Not the sudden darkness of a power outage, not the sharp black of a closed door. Something gentler than that, a fading, like the last ember in a fire that has been burning all night, growing smaller, softer, until you are not sure whether you are still seeing it or only remembering it. This is what astronomers sometimes call the degenerate era, a time when the universe still contains matter, but no new light is being made. The great furnaces have all gone cold. What remains are the remnants, white dwarfs, those dense and quietly glowing cores left behind when stars like our sun exhaust themselves. They will still be there, holding their heat, radiating it away into the dark, but so slowly. White dwarfs cool over timescales far longer than the current age of the universe. A white dwarf born today would still be faintly warm trillions of years from now, dimmer than a candle seen from across an ocean, but not yet gone, not yet fully dark. They are patient objects, the most patient objects in the cosmos, holding the last warmth of stars that lived and died before the darkness came. But even patience has a limit. Over spans of time so vast that numbers lose their meaning, the white dwarfs will cool further and further until they radiate nothing at all. They will become black dwarfs, cold and invisible, drifting through a universe that has forgotten what light was. No black dwarf has ever existed. The universe is far too young for that. It takes so long for a white dwarf to fully cool that the process has not yet finished for a single one. Not anywhere, not once, in all of cosmic history. And yet, someday, they all will. And then, something even stranger may happen. Given enough time, the very matter that makes up these remnants may come apart. There are theories, still uncertain, still debated quietly among physicists, that protons themselves are not eternal, that over timescales of perhaps 10 to the power of 40 years or more, even protons decay, dissolving into lighter particles, into radiation, into nothing solid at all. If this is true, and we do not yet know for certain, then eventually there will be no atoms left. no matter in any form we would recognize, only photons, drifting without purpose through the expanding dark. Neutrinos, barely interacting with anything, passing through the emptiness like ghosts that have forgotten what they are haunting. And black holes, the last great structures, sitting alone in the void. Black holes. They seem like the end of everything. Places where matter falls in and never returns. But even black holes are not permanent. In 1974, Stephen Hawking proposed something remarkable. He showed that black holes radiate, not brightly, not in any way you could see or feel, but faintly, impossibly faintly, through a process now called Hawking radiation. Quantum fluctuations near the event horizon allow particles to escape, carrying away the tiniest amounts of energy, and with that energy, the tiniest amounts of mass. The temperature of this radiation depends on the size of the black hole, and the relationship is an inverse one. The larger the black hole, the colder it radiates. A black hole with the mass of our sun would have a Hawking temperature far below the current cosmic microwave background, so faint, so cold, that it is effectively colder than the space surrounding it. It absorbs more from the universe than it gives back. Supermassive black holes, the kind that sit at the centers of galaxies, are colder still. Their Hawking temperatures are on the order of trillionths of a degree above absolute zero. Almost nothing, almost silence. Right now, in the present universe, black holes are among the coldest objects that exist, colder than the space between stars, colder than the faint hum of the cosmic background. But here is where the story turns. As the universe continues to expand, the cosmic microwave background continues to cool. It is 2.725 Kelvin now, but it will not stay there. It will drop, slowly, over billions and trillions and quadrillions of years, falling towards zero, but never quite arriving. And at some point, the temperature of the background radiation will fall below the Hawking temperature of the remaining black holes. And when that happens, for the first time, the black holes will be warmer than the space around them. They will begin to lose more energy than they absorb. They will begin, very slowly, to evaporate. The last black holes in the universe, the supermassive ones, will take an almost incomprehensible amount of time to vanish, roughly 10 to the power of 100 years, a 1 followed by 100 zeros. A number so large that writing it out would fill pages and still convey nothing of its true scale. But even that number is finite. And so, eventually, the last black hole will radiate its final particle and disappear. And with it, the last significant source of warmth in the universe will be gone. What remains after that is a cosmos of maximum entropy, a state where energy is spread so thin and so evenly that nothing can happen. No heat can flow from one place to another because there is no difference in temperature anywhere. No work can be done. No structure can form. The temperature of everything approaches zero, not reaching it, never quite reaching it, but drawing closer and closer, like a curve that bends toward a line it will never touch. This is the deepest cold the universe will ever know. Not a place, but a time. An era of stillness so complete that the word stillness barely holds it. And here, at the very edge of what temperature means, the concept itself begins to dissolve. Temperature, as physicists define it, is a property of large collections of particles. It describes how energy is distributed among them. A single atom drifting alone through the void does not have a temperature. It has energy, it has motion, but temperature is a collective idea, and when there is no collective left, the idea has nothing to describe. At the quantum scale, where individual particles are all that remain, temperature loses its footing. It becomes a word without a referent, like asking what color silence is. There is one more quiet strangeness worth knowing. In certain laboratory conditions, physicists have created systems that are said to have negative temperatures. This sounds as though it means colder than absolute zero, but it does not. Negative temperature describes an inverted distribution of energy, a state where most particles occupy higher energy levels rather than lower ones. It is not a deeper cold, it is something else entirely. In fact, Systems at negative temperature are thermodynamically hotter than any system at positive temperature. They will give energy to anything they touch, no matter how warm. It is a reminder that temperature is not a simple ladder from cold to hot. It is something more subtle, more circular, and at its extremes, more strange than our everyday experience would suggest. But that strangeness belongs to laboratories and equations. Out here, in the long future of the universe, there is only the quiet, the slow, patient cooling that has been underway since the very first moment. A universe that began in unimaginable heat, gradually, gently, letting it go. And perhaps, before the stillness settles completely, it is worth returning to something familiar, something close to home, that connects the cold of the cosmos to the cold you may have felt on a winter morning. When you open a pressurized can, a spray of air or gas rushes out, and the nozzle turns cold against your fingers. This is not a mystery, though it might feel like one. It is the Joule-Thomson effect, a principle discovered in the 19th century and still at work in nearly every refrigerator, every air conditioner, every quiet hum of cooling machinery in the world around you. When gas expands, it spreads its energy across a larger volume, and in doing so, it cools. The molecules move apart, their collisions become less frequent, and the temperature drops. It is a gentle exchange, pressure traded for cold, motion traded for stillness. And this same principle, scaled up beyond anything we build on Earth, is what makes the Boomerang Nebula the coldest known natural place in the universe. A dying star, exhaling its outer layers at tremendous speed, roughly 164 kilometers every second, pushing gas outward into the void. That gas expands, and as it does, it cools, just as the air from a pressurized can cools your hand. But here, the can is a star, and the room it opens into is the universe itself. The result is a temperature of about 1 degree Kelvin colder, even than the faint warmth that fills all of space. A cosmic refrigerator, running on nothing but expansion and time. It is strange to think that the same physics behind the hum of your kitchen also governs the coldest place we have ever found among the stars. Now, on Earth, cold is something we feel in more ways than one. On a winter night, the wind pulls heat from your skin faster than still air would, and the temperature seems to drop. Though the air itself is no colder, this is a wind chill, a measure of how quickly your body loses warmth, not a measure of the air's true temperature. It is a human experience of cold, shaped by motion and contact. But in space, there is no wind, no air pressing against a surface, no breeze to carry warmth away. Heat can only leave an object through radiation, the slow release of infrared light into the dark. This is why cooling in space is patient, unhurried, a process measured not in moments but in centuries or longer. And this leads to one of the quieter lessons the universe offers. Temperature and heat are not the same thing. High above the Earth, in the layer of atmosphere called the thermosphere, the sparse molecules of gas can reach temperatures of 2,000 degrees Celsius. And yet, if you were there, you would feel cold, profoundly cold, because the gas is so thin, so spread out, that there is almost no heat to transfer. The molecules are fast, but there are so few of them that they carry almost no energy to your skin. A thermometer would read thousands of degrees, but your body would radiate its warmth into the emptiness and feel nothing but the chill. Temperature tells you how fast particles are moving. Heat tells you how much energy is actually there. They are related, but they are not the same. And the cold universe teaches this distinction quietly in the thermosphere, in the voids between galaxies, in the thin winds of dying stars. To speak about cold with precision, science needed a scale that began where cold begins, not at the freezing point of water, which is an accident of chemistry, but at the point where thermal energy itself runs out. In 1848, a man named William Thomson, later known as Lord Kelvin, proposed such a scale, drawing on the earlier work of Sadi Carnot, who had studied the flow of heat in engines. Kelvin imagined a thermometer that started at the lowest possible temperature, the point we now call absolute zero, and counted upward from there with no negative numbers, no arbitrary landmarks, just a clean measure of how much thermal energy a system holds. The Kelvin scale begins at zero, and that zero means something. It means nothing is moving, or as close to nothing as the laws of physics allow. It is the natural language for cosmic temperatures. The only scale that does not pretend cold has a middle. For a long time, the Kelvin was defined by a single physical event, the triple point of water, the precise temperature at which water can exist as solid, liquid, and gas all at once. 273.16 Kelvin. That delicate balance point anchored the entire scale. But in 2019, the definition was changed. The Kelvin is now defined not by water, but by a constant of nature, the Boltzmann constant, a number that links temperature directly to energy at the most fundamental level. It is a quiet shift, but a meaningful one. Temperature is no longer tied to a substance. It is tied to the fabric of physics itself. And with that understanding, one final truth comes into focus, slowly, like a star dimming over billions of years. Entropy always increases in an isolated system. This is the second law of thermodynamics, and it is among the most unbreakable rules we know. It means that energy spreads out, that differences in temperature even out, that every hot thing slowly shares its warmth with its surroundings until there is nothing left to share. The universe is an isolated system, as far as we can tell, and so it is cooling. It has been cooling since the first moment, since the unimaginable heat of the Big Bang began to spread and thin and fade. Every star that burns is spending an inheritance that will not be renewed. Every galaxy that shines is a temporary arrangement, a brief warmth, and a long, long night. The arrow of time itself, the reason we remember the past but not the future, the reason eggs break but do not unbreak, may be connected to this universal drift toward cold and disorder. Time moves in the direction of increasing entropy, and increasing entropy means cooling, spreading, quieting. Every warm object in the universe is temporary. The stars, temporary. The planets, temporary. The faint glow of the cosmic microwave background, still fading, still cooling, still dimming toward a silence it will never quite reach. And every cold place, every shadowed crater, every dark nebula, every still and frozen world drifting far from any sun is not an anomaly. It is a glimpse, a quiet preview of what everything will eventually become. Not with violence, not with spectacle, just the slow, patient, irreversible release of warmth into the dark. This is what the cold places teach. If you listen carefully enough, they are not the absence of something. They are the presence of the future, written in frost and silence, waiting. And yet, the cold places are not empty. They are not barren, not lifeless, not the end of anything. They are full, quietly, patiently full, of physics that only reveals itself when everything else has been stripped away. In the warmth of ordinary life, matter behaves in familiar ways. Atoms bounce and collide. They jostle and spin. They are restless, individual, separate, each one a tiny point of heat doing its own small dance. But cool them down, slowly, gently, and something changes. The jostling slows. The collisions soften. The atoms begin to settle. And in that settling, in that deepening quiet, new rules emerge. Rules that were always there, hidden beneath the noise. Cold is not the absence of something interesting. It is a different kind of stillness. A stillness where the universe begins to whisper things it cannot say when it is loud. Cool an atom far enough, down past the temperatures of interstellar space, past the faint warmth of the cosmic background, down into the millionths and billionths of a degree above absolute zero, and the atom begins to change. It stops behaving like a point, a particle, a small hard thing bouncing off other small hard things. It begins to spread. Its position becomes uncertain, not because we cannot measure it, but because it genuinely does not have a single position anymore. It is here, and here, and here, all at once. A smear of probability, a whisper of presence spread across space. This is the wave nature of matter, something predicted by quantum mechanics, something confirmed again and again in laboratories on Earth, but something that only becomes visible, only becomes real in any tangible sense, in the deepest cold. Cool, a cloud of atoms to within billionths of a degree of absolute zero, and the individual waves begin to overlap. The boundaries between one atom and the next start to blur. They are no longer separate things. They are no longer a collection. They become something else, a single entity, a single wave, thousands of atoms breathing together as one. This is a Bose-Einstein condensate, a state of matter that exists nowhere in nature, that has never formed on any world or in any nebula, that can only be coaxed into being by the most patient and precise cooling humanity has ever achieved. And in that state, the universe shows a face it shows nowhere else. The deepest cold does not destroy complexity. It transforms it. It trades the busy chaos of heat for something stranger, something more unified, something almost serene. And this is what the coldest places teach, not just in laboratories, but across the whole of the cosmos. That cold is not a void. It is a canvas. In the cold cores of molecular clouds, where temperatures hover near 10 Kelvin, complex molecules form on the surfaces of dust grains, organic compounds, the building blocks of chemistry that will one day become the building blocks of life, assembling themselves in silence, in darkness, in cold so deep that light itself is swallowed before it can escape. In the frozen craters of the moon, where sunlight has not reached for 2 billion years, water ice persists, quietly, patiently, waiting for nothing, expecting nothing, simply enduring. In the Boomerang Nebula, where gas rushes outward from a dying star and cools below the temperature of the universe itself, there is a kind of transformation happening that exists nowhere else in nature, a place colder than the space around it, colder than the faint afterglow of creation, a place that should not be, and yet is. Cold is where the universe does its quietest work. In the universe, all of it, every star, every galaxy, every photon still traveling from the first light, has been on a journey toward that quiet since the very beginning. It began in heat beyond description. In the first fraction of a second after the Big Bang, temperatures were so high that the numbers lose all meaning. Trillions upon trillions of degrees, a universe so hot that matter itself could not hold together, that the forces of nature were merged into a single undifferentiated fire. And then it began to cool. Not suddenly, not dramatically, just steadily. The way a stone cools after a long day in the sun. The way breath fades from a window on a winter morning. The universe expanded, and as it expanded, it cooled. The plasma thinned. The light stretched. The temperature dropped from billions of degrees to millions to thousands. In about 380, 000 years after the beginning, the universe cooled enough for atoms to form, for light to travel freely for the first time, and that light is still traveling now, still cooling, still fading. We call it the cosmic microwave background. It fills all of space, every corner, every void, every shadow. It is the oldest light in the universe, and it carries a temperature of just 2.725 degrees above absolute zero. It has been cooling for 13.8 billion years, and it will continue to cool for billions more, for trillions more, for longer than any number we use in daily life can hold. The universe is on a journey towards stillness, and it has been on that journey since the first moment. And somewhere tonight, far away in the constellation Centaurus, the Boomerang Nebula is still there, still expanding, gas still rushing outward at 164 kilometers every second from a star that is slowly dying, still cooling the space around it to just 1 degree above absolute zero, colder than the background hum of creation itself. A small pocket of extraordinary cold in an already cold and cooling universe. It does not know we have measured it. It does not know we have given it a name. It simply continues, expanding, cooling, quietly becoming what it is becoming. And all around it, in every direction, filling every gap between every star and every galaxy and every void. The cosmic microwave background hums, so faint that no human ear could ever hear it, so cold that no human hand could ever feel it. But it is there. It has always been there, since the universe first became transparent, since the first light was set free. A warmth from the very beginning, stretched thin across 13.8 billion years, still arriving, still passing through this room, through you, through everything. A lullaby. From the beginning of time, still playing, still fading, and the cold deepens, gently, as it always has.